Hi, Chapter 9 is all about sequences and series. So in this first section, we're just going to try to work on noticing patterns and continuing them. So I do want you to actually do these first 5 on your own. So go ahead and pause that. Alright, so the first one you were adding 4 each time, so you should end up with 23 as the next term. On number 2, you were multiplying each number by 3 to get the next term. So when I do 54 times 3, I get 162. Number 3 is just my name, so it should be K for Pack. Number 4, you did minus 3, minus 6, minus 12, minus 24, minus 48. So I should be, sorry, minus 24 is the last one. Then I should be doing minus 48 to get to this next one, which would be 7. So you were subtracting a number, and then just the next time you subtracted twice that much, and the next time you subtracted twice that much. On number 5, you are adding each time, but you are adding your odd numbers, so like plus 1, plus 3, plus 5, plus 7, plus 9, and then plus 11 would give me 34. Some sequences are defined explicitly, so with this definition that you're seeing here for A, B, and C. So I want you to find each of the first 4 terms of these sequences. So on A, to find A sub 1, or my first term, that's going to be 3 times 1 minus 2, which would just be 1. A sub 2 would be 3 times 2 minus 2, which would be 4. Go ahead and do A sub 3 and A sub 4. Okay, you should get that A sub 3 is 7 and A sub 4 was 10. On B, same thing. When I do A sub 1, I'm going to do 3 plus negative 1 to the first power. So that would just be 2. Go ahead again, pause it, do the next ones. Okay, you should have gotten that A sub 2 was 4, A sub 3 is 2, A sub 4 is 4, and it should keep flipping back and forth like that, and that's because of this negative 1 here. Each time you're either adding a positive 1 or a negative 1, so I can only be going back and forth between those two numbers. For A sub 1 down here, you should be doing negative 1 to the 1 over 2 times 1 minus 1. So that should be negative 1 over 1, or just negative 1. Go ahead again, pause, and do the second, third, and fourth terms. For A sub 2, you should have gotten 1/3. A sub 3 should have been a negative 1/5. A sub 4 should have been 1/7. It would be okay to use decimals, except that 1/3 is a never-ending, and it's repeating, and I'm only okay with decimals if they end, and you can actually write the entire decimal, so fractions. Sometimes I'll ask you to find the nth term, so you would actually need to write an expression and then use that to find the nth term. So if I don't tell you what type of sequence it is, which I haven't taught you those yet, that'll be later, then we need to start looking at maybe how our term number, so this is the term number, relates to what the actual number is. So my first term is 1, my second term is 3, my third term is 5, my fourth term is 7. I'm trying to figure out the patterns so that I can figure out what my nth term is. I mean, I know I could do times 1 here. If I did, these are all going up by 2 each time, and actually these numbers on the bottom, my actual numbers, seem to be 1 less than double the top number. So if I did like 2 times this number minus 1, I would get 3. 2 times 3 minus 1 is 5. 2 times 4 minus 1 is 7. So I'm doing 2 times my term number minus 1. So when I write out my formula, it's 2n minus 1. Go ahead and try B on your own. Make sure you start by writing out the term number and then what the term was. If you're not noticing a pattern, start looking for it. Is the number down here close to anything that I can get from doing these, something to all of these numbers up here. And I noticed like with the 17 and the 10, I mean those are close to like 16 and 9, and this is just one more than 4. It's almost like you squared the first number, squared your term number, and added 1. So my explicit form or explicit expression would be a sub n equals n squared plus 1. Alright, this next sequence is called our Fibonacci sequence, and it's what's called a recursive sequence. So when we are writing our definition for it, our definition includes using the previous term. In this particular sequence, we're actually using the previous 2 terms. So here's my term 0, term 1. When I want a sub 2, this is going to be a, and then I'm going to do 2 minus 2, so a sub 0, plus, and then 2 minus 1 would be 1. So I'm going to do the 0 and the first term together, so 1 plus 1, which is 2. For a sub 3, you would do a sub 1 plus a sub 2. So that'd be 1 and 2 together, which is 3. So far we have 1, 1, 2, 3. Go ahead and actually give me the next 3 terms of this sequence. Should be 5, 8, 13, and then you could keep going. This link actually takes you to some cool examples, of the Fibonacci sequence happening around, like in real life. It's not working for some reason from here, but you should go and look at it. It's really actually quite cool. Next thing we're looking at is factorial. So that's your exclamation point, and that's basically if you have any positive number n. So let's say if I had 6, I would do 6 times, and then 1 less than that is 5. And 2 less than 6 is 4. I'm going to keep doing that until I get down to 2 and 1. So I keep going all the way until 1. And there is the special case of 0 factorial, which is equal to 1. So here when it says find the following, 3 factorial is 3 times 2 times 1, which would be 6. 5 factorial would be 5 times 4 times 3 times 2 times 1, which would be 120. Okay, go ahead and see which of these you can do on your own. As you're looking at C and you're writing everything out, notice I've written everything out for all of them so far, so you should also be doing that. I kind of ran out of room to go all the way from 7 down to 1, so I just went 7, 6, and then dot, 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 implying that would be 5, 4, 3, 2, and then 1. Same on the bottom, but because I'm multiplying here, 7 times 6 times 5 times 4 times 3 times 2 times 1 is on top and bottom, and that would cancel. So I can mark those off. I really just have 12 times 11 times 10 times 9 times 8, which would be 95,040. I would do that for each one so that you can cancel what you need to. You end up with 56 over 2, which is 28 for D. My 5 through 1 would cancel, and then this 2 and 1 would cancel, so I'm actually left with just 6 over 3, which is 2. On F, if I did n factorial, that would be n times whatever 1 less than that is, times whatever 2 less than n was, all the way down until I get to 1. For n minus 1 factorial, I'm starting with n minus 1, then it would be n minus 2, then it'd be n minus 3, and I'd keep going all the way down to 1. This n minus 1 times n minus 2 all the way down to 1 would cancel for the top and bottom, and so you would just be left with n as your answer. That's where writing these out really kind of comes in handy. Finding the terms of a sequence involving factorial. So find the first 5 terms of the sequence given by this explicit expression, beginning with n equals 0. So for a sub 0, I'm going to do 2 to the 0 over 0 factorial. 2 to the 0 is 1, 0 factorial is 1, so I have 1 as an answer. For a sub 1, that's going to be 2 to the 1 over 1 factorial. 2 to the 1 is 2. 1 factorial is 1, so 2 over 1 is 2. Keep going with that. Since I want the first 5 terms, go all the way to a sub 5. Even though we have a sub 0 here, I want you to go all the way to a sub 5. Right, so you should have gotten a sub 2 is 2, a sub 3 was 4/3, a sub 4 was 2/3, and a sub 5 was 4/15. Alright, summation notation. So this is where you're taking the first however many terms, or maybe the middle terms, or a certain number of terms, and you're adding them together. So when I have this right here is written as the sum from 1 to 5 of 3 times I or x, whatever that number is. Here we use I here, so it's 3 times I. This is not your imaginary I. This is an I within my summation notation. So when I do that, first I should probably list out my terms. So I'm going to have 3 times 1, 3 times 2, 3 times 3, going all the way to 5. So 3 times 4, and 3 times 5. It's a summation, so I'm adding all of those together. So that's 3 plus 6 plus 9 plus 12 plus 15. Which, when I add all of those together, I get 45. So my answer here is 45. Do the same thing for B. Set up each of your terms, so plugging in all the numbers from 3 to 6, all your integers from 3 to 6. Actually find out what those terms are, and then add them all together, and you should get 90. Go ahead and do C. As you're doing C, as far as what I need to see, would just be like 1 over 0 factorial plus 1 over 1 factorial, and then you can go all the way through 8, and then you can just type those in and get those numbers and write them out here. I would recommend probably using fractions. When you add all of those up now, which I would just put in my calculator 1 plus 1 plus 0.5, and then I'd probably start putting parentheses around it, you should end up with 2.71827. I mean, it keeps going, but right there is okay. I don't necessarily need that part as a fraction, because this is going to become so ugly, and I wouldn't expect you to have a denominator quite that large and leave that as your answer. Alright, our series. So your series is your sum of all of your terms of an infinite sequence is your infinite series. The sum of the first n terms of a sequence is called a finite series, or your partial sum. So for this series, I want you to find the third partial sum. So you're going to find the sum of the first 3 terms. So when I add each of those together, I get 0.333. If I'm doing the infinite sum, so if I keep doing this forever and ever and ever and ever, it would be 0.3333 repeating, or 1/3. So do think through that when you're doing your infinite series.